Good morning and good evening. I would like to give a talk, joint work with Philippe Jacquet from India and Shamir from Google on precise minimax regrets. This work was initiated in Google when I visited GIL. So let me start with a very general overview. We are dealing with online learning when data are received sequentially and are used to update predictors. We do it in supervised online setup, which means that the model is trained from data that we have already received. More precisely, we have capital T rounds. At time t, we predict label y sub t, knowing all labels up to time t minus 1, and features up to time t. That is it is known as improper learning. When we do prediction, the system reveals the real labels, and we incur loss, and we will consider only logarithmic loss. Finally, one word about notation. We will use t as running parameters for rounds, capital T as the total number of rounds, and we use superscript y to superscript t as a sequence of labels y1, yt, the same we do with respect to features. Let's make it more precise. This is a game between nature and learner. At each round, the learner obtains a d-dimensional feature vector, xt, and makes a prediction that we denote yt hat. Then the nature of environment reveals the real label, which is assumed to be binary minus 1 and 1, and we incur loss, L y hat y. At time t, the total loss up to capital T is sum of all losses, which is the first term here, but instead of doing absolute loss, we will do relative loss or pointwise regret when we compare total loss to the best loss that can be obtained for the best predictor F that's coming from a class of predictors. So in this work, we're actually focusing on maximal minimax regret when we'll be looking for the best predictor for the worst sequence of labels of the pointwise regret. That's what we will try to study. Okay, now I will be more specific about the model that we consider in the paper. First of all, we consider only linear predicted. F is a scalar product of the feature and the weight vector that we will update in some way. We are not discussing this paper how to update it, where this is a scalar product. As the loss function, we consider only logistic regret, so log of 1 plus exponent, labels, and the scalar. We also have another important view. We're actually assuming that the prediction comes from some learning distribution, for example, Bayesian averaging or Bayesian mixing. And then the pointwise regret in this setting is sum of logarithm of learning distribution and the comparator. The minimax is the same pointwise regret, but for the best distribution, learning distribution, and for the worst label sequence. Please notice that this minimax regret constitutes a universal lower bound for all pointwise regret. Doesn't matter what kind of learning distribution you use, Bayesian or not, which we are not assuming in this paper. In our model, in this particular paper, we assume that the features take only n distinct discrete values, a sub j, with each a sub j is a d-dimensional vector, and each element of the vector belongs to a finite alphabet of unspecified size. Notice then that the t rounds are split into n different rounds, and t sub j is the number of t such that aj feature is used. In this situation, the total loss as again defined the same way. However, for the finite number of features, it has a little more complicated formula, but this is exactly the same when I specify that each of them can take only n values. So that's what we'll study with relative regret. Finally, since we're considering only binary levels, the logistic regret could be connected to the probability of the level y, as you can see it here. And it is actually inverse of the logistic regret. When again, there are two parameters, y of t and x of t. So x of t can take n different values. I can split this as a product, the total probability from from y1 to yt as a product with respect to n, so different values of the features. However, we also have to consider that y of t can be 1, and I'm assuming that k sub j of t sub j rounds have y equal to 1 or minus 1 as here. And this is the probability that we will be estimating. Again, the pointwise regret, I repeat it here with this provision that I show you here. In particular, it is log of the supremum over learning distribution. Our job is to find actually how the supremum behaves. And I remind you that in the minimax regret, we again trying to find the best level, the best learning distribution for the worst levels of the pointwise regress. This representation is not the best to estimate our probability, especially the supremum of the probability, and this is not the best computational expression. So we will go to information theory tools and express this minimax regret as the Sztarkov sum. First of all, I define maximum likelihood distribution, P star, as a supremum of all probabilities normalized. This red sum is important, and we call it Sztarkov sum. And I will show you that this is actually minimax regret that equal to the Sztarkov sum. So let me repeat the definition of the minimax regret, the first line here. Notice that supremum maximum can commute. So when I commute it, put it here, and this is my definition of minimax regret. Now I do a small trick. I add and subtract log of this sum, which is this denominator here, normalizing sum. So by the way, the minus this is here in P star. Okay, but now I will choose Q, the optimal learning distribution equal to P star. So this is 0, and what is left is basically log of the Sztarkov sum. So the minimax regret is log of the Sztarkov sum. I will denote it by dt. And this what we would like to estimate. This is actually quite complicated sum, and especially the logistic regression. So before I go into this, few comments. First of all, minimax regret was introduced universal compression, and our model fits into this universal compression for d equal 1. Work from Davison, Krichevsky, Triphaumov, Risanand, and with Michael Demota, we put actually everything around and a comprehensive analysis of this. For fixed M is the size of the alphabet. When M is large, Orlitsky-Santaman provided the Perth analysis for some ranges. Shamir also did it. And with Marcello, we provided precise estimates for all ranges of M. When D is greater than 1, situation is different. And Bayesian algorithm was used mostly for Boston regret. So some Bayesian averaging. I think the best paper in this area starting is Kakada and in 2005. Foster generalized it to multi-levels, and Shamir actually did it for RD. Minimax regret, I think we started with Gil introducing it. This paper provides the first precise analysis when there you have finite featured values. The closest to what we have is the one by Rachling and Sridharan, but they do also maximum over all features. So here finally is our result. Again, there are n featured values. PW is a regression function. And for n not growing faster than log t and finite d, we prove that the minimax regret grows like d half log t, as expected. There is a constant. But the second constant here is much more complicated. It's integral over square root of determinant of a matrix expressed here. And this is usually hard to compute. For example, for special case when they equal 1, and then you have n different distinct values, this constant looks quite complicated, but computable in certain situations. Again, D is fixed here. We generalize it to the situation when you have m levels, so the weighting vector becomes weight matrix, the logistic regression becomes soft function, as in Foster paper. And now we have m different levels, not just 2. As again, for the same restrictions, we prove that we have similar growth, and m minus 1 appears in the first leading terms as well in the integral. This matrix is much more complicated, and I will not go into this, but you can see that the expression for the constant is quite complicated. As the final statement, and in anticipation of the question, can we generalize this analysis to features that are continuous in a bounded interval? Like, for example, features belong to 0, 1 interval. We claim that yes, and we believe the result is have similar leading function d half log t. The constant here depends on d dimension as well as the feature value. For some special feature value, for example, laying on a d-dimensional sphere or ball, we're able to compute it for large t. Thank you very much.